Hi there, this is Chris, and I'm going to do a walkthrough of assignment 1, which is the first assignment that's going to involve a bit of coding and reading code, and our first real assignment in 107. So let's just get straight into it. What I'll do is I'll go over some the actual assignment, all the different parts, and I will explain some of the things you might need to consider when you're doing the assignment. All right, so here's how it goes. I pulled up the assignment just from Course Materials, Assignments, Assignment 1, and this is the assignment. A couple things to start off with. First of all, it's due next Monday at midnight. I'll talk a little bit about the on-time bonus later, but basically if you get the assignment in on time, we give you 5% extra. If you do need to take extra days for being late, you don't get the 5% bonus. All right, for this assignment, obviously the learning goals are going to be more or less the same as with the lab, and we're going to be talking about bit operations and number formats, and you're going to do lots of practicing with writing code and reading code to do that. Okay, the assignment itself, it has basically 6 different parts to it, and each one has tests a little bit different set of all of the bit operations and the number representations and so forth. And some of it is actually writing code, and a lot of the rest of it is reading code. So you're going to do a little bit of both. And this will also give you a little bit more information about the C programming language. So I can tell you right now that none of the programs you have to write should be long. We're talking about short functions. The sample solutions generally don't have more than about 15 lines of code in them total. You do not need any helper functions. You do not need to make the code long. Okay, so you should be thinking short, and you should be thinking, I just need to do a few things, and that's it. Okay, a couple of comments on collaboration. This is an assignment where you should really work alone. You can talk about big ideas with other people, but you really don't want somebody to say, hey, you should do it this way, because that gives away the thought process. Like, in other words, you don't get to think about it, and there's some things that once you work through them and actually think about them and write some examples down and try them on your own, you're going to learn them. Otherwise, if someone says, oh yeah, you need to think of this trick to do this, then you won't really learn the information. So no collaboration on this one aside from possibly big ideas. Okay, you should definitely not be looking at anybody else's code, nor really talking about other people's code. All right, so to start out, I'm going to clone the assignment just like we would do. So if I SSH into myth, then all right, and then I happen to have a 107 folder, and if I type the clone, I just pasted it from there, and we have our assign 1 folder. All right, so let's actually look at, by the way, a couple things in here. There's a samples folder, which is all of our solutions that you can run, and you should make your code match our solutions. And there's a makefile and all of your C code and a readme txt file and so forth. Okay, so and there's also a custom tests file. Custom tests right now has a couple of tests in there that we've created for you, but you should add to that. And when you do sanity check, you can run sanity check on the custom tests, and it will test your code. It'll run those tests for you. Okay, so let's go back to the first part of the assignment. Okay, the first part of the assignment is a relatively straightforward power of 2 part of the assignment, and what you're going to do is you're just going to basically look at this little definition right here and figure out what it's doing and why it's doing it. Okay, I'm not going to go into too much more details, but basically just answer these questions about it, and you need to think about number formats and what's actually happening with the and operator, bitwise and operator here, and what happens when you compare that whole thing to 0 using equals equals and so forth. So you want to be able to figure it out. Now, of course, we give you a little bit of an idea of what it does. The question is, why does it do it? So that's the first part of the assignment. Okay. Second part is about finding the midpoint between two variables. Okay. If you notice, and definitely read this about the overflow bug, it's very interesting. The idea is that you might think that finding the average between two values, in other words, the midpoint, would be as simple as saying low plus high divided by 2. Problem is, low plus high has the potential to overflow. Why? Because if the numbers are bigger than int max, it will actually overflow. Okay, so we want to figure out if there's a better way to calculate the midpoint between two numbers without dealing with this issue of overflow. Kind of neat. Okay, well, it turns out there are better ways. Okay, one of them is to just do this. First, calculate high minus low, divide that by 2, and then add low. If you try out a few examples, you'll find out that that gives you the midpoint. Okay, and here's another one, which first does some interesting casting. It casts the values, high and low, to unsigned ints, does some calculations on them, or actually adds those values together, and then does this shift, by this right shift by 1. And that's interesting too. All right. And then finally, we have a really crazy one here, which does some interesting bitwise arithmetic and comes up with the midpoint. And your job is to figure out what's going on. This one was actually described first by our own Donald Knuth, and it is a very interesting way. But I'm not going to tell you what to look for here, except to say that try some examples, try to actually see what's going on with the bits, write out all the bits, do it on short examples, right? Do it on an example that you know the answer to with 4 bits or maybe 8 bits. And try it out for a few different ones and convince yourself, A, that it works, and B, start to think about why it works. The one hint I will give you is definitely remember that 2's complement numbers, it's just the bits that actually, or the actual bits are powers of 2. Okay, so if you think about that and you think about what's happening with these powers of 2 when you're taking an average, you'll be able to figure out what's going on with that. Okay, so that's read some code and answer some questions about that. All right, the third one, also another read some code here, is an interesting, it's an interesting way to figure out if any bytes in a particular integer are 0. Okay, you might think to yourself, well, one way to do that is I could loop through all the bytes. You could, but this is a much, much faster way. In fact, it's significantly faster and uses some of these bitwise tricks that you can use. Do recall that if I take the complement of a number, it returns all ones, so that's something you might want to think about. And just remember what your bitwise operations do for shifting and for and so forth. Okay, so you're going to have to do some describing for that. So far we haven't had to write any code. It's just been reading code and trying to understand it by playing around with the numbers, seeing what's actually happening, understanding what the bit patterns are that are produced, and understanding what the actual code is doing because of some of these somewhat difficult to parse but interesting bitwise operations. Okay, all right. Now, for the other code writing programs, now these are the final code writing programs: the Saturating Arithmetic, the Cellular Automata, and UTF-8. We've actually written a fair amount of code for you that does some of the kind of the underlying conversions and things, or the printing and the actual underlying things. What we want you to do is, first of all, read it all, read all the code, and second of all, we want you to actually comment the starter code, the parts that we have written. Don't change the code at all, just comment the parts that we have written. Now, why are we asking you to do that? Well, it's because we want you to start to read C code. And we want you to start to like think about, oh, this is how we might do all of this printing out with printf and so forth. So please review the material and then go ahead and comment it. So part of the grade is going to be on commenting the starter code as well. Okay, so some of it, by the way, on assignment 0, we asked you to use the ATOI function, and that converts ASCII to integer. That's what that stands for. But it wasn't very robust. I don't know if you remember, but it didn't work on it didn't work on strings, didn't give you a return value that was interesting. It just basically said, if I can't figure it out, I'm returning 0. There's another function called str2l, string to long, which actually is much more robust. It allows you to put things like hexadecimal numbers and so forth, and it is able to do the conversion. But you have to figure out how it actually works. So go ahead and do man strtol and see what it actually says. If you go over here and do man strtol, you can actually see, and it tells you where to find it. It tells you what it does. And it says the function converts the initial part of a string to a long integer in a given according to a given base, etc. And it can allow white space, and it can allow, as I said, lots of other interesting conversions. More robust, harder to kind of understand, so you have to look through and see actually what it's doing. Okay, you should understand str to long to the point where you could answer these questions here. Okay, like how is the second argument used, etc. What's the error function, and so forth. Okay, all right. Remember, you're commenting the starter code too, so you're going to have to at least know enough to figure out what's happening in the starter code. Okay, we can even take a look at that here. Let's look at the first one here, saturating sat.c, and these are some of the functions you have to write. But remember, you're not going to edit this code, but you're going to actually look at, and there's the string to long. You're going to need to know that. Figure out what the error function does, and so forth. You're going to comment main, and you're going to put good comments in there. Okay, you don't have to write this, but you have to comment it. Okay, so let's look at the saturating arithmetic program. So this program is interesting in that what we're trying to do is we're trying to say, all right, if I am going to add two numbers together, well, we know from lecture that if we add two numbers together, then there's a potential that it can overflow. And what this saturating add is going to do is, instead of letting it overflow, it's going to cap the number at the maximum. So if it would overflow, it's just going to return the maximum, the int max for that particular type. Okay, and so in this case, we're actually going to do sat, and then let's say we do 8. And by the way, you can test all this on the samples, right? If I do samples sat solution 8, well, guess what? It gives you the output like the output over here, right? If I type sat 8, 126, and 5, well, we can do sample sat solution 8, 126, and 5. Well, the maximum integer is 127, so 126 plus 5 would overflow, and therefore it gives you the value of 127 because that caps it. It saturates it, as we say. By the way, we use this in things like volume controls, or in various graphical situations where you're dealing with colors. The volume one is one that I've used before, where you want to, like, if you keep increasing the volume, I don't know if you've ever used like a radio or something where you keep cranking the volume button, and it keeps going and keeps going, but the volume ends up stopping at some value. Okay, 11, as they say. But anyway, the point is that this is what that function is going to do. Okay, so you have to implement a few different functions here. You have to implement the function signed min and signed max, and given the actual bit width. Okay, so that should tell you the bit width, or that should return the smallest and largest, the smallest for signed min and the largest for signed max values. So you have to write that, and then the sat add function is going to actually take the bit width and then 2 operands and actually produce the values. Okay, so you don't have to write any other functions. You don't have to write any helper functions or anything like that. And keep in mind, these functions are going to be relatively short. Okay, they just need to do what we've asked. They don't need to go and do anything else. All right, a couple of restrictions on this. Well, you're not allowed to use any of these comparisons. You're not allowed to. Okay, and there's no special cases on the bit width. All right, you're not allowed to use, well, first of all, your functions have to use one code path. And so in other words, you can't say, if it was 4, do this, if it was 8, do this, if it was 16, do this. Not allowed to do that. Okay, you have to just have it act on the number as the number using our bitwise operations and bitwise logic. Okay, so don't do that. If you do break these violations, you're just not going to get any credit for that, this part. Okay, don't use the special ones. We want you to think about this in terms of the bitwise operations. That's what this whole assignment's about. Okay, so that's that one. The next one, this is an interesting one. If you were in cs106b and you did the game of life assignment, this will be relatively similar in thought to the game of life assignment, except now we're going to actually do it using, well, bit operations, and we're going to do it in 2 dimensions instead of 3 dimensions. So in some sense it's slightly less intense. In other sense it's you're going to actually have to use some new logic to get this done. Okay, if you did the Photoshop assignment, you will see similar ideas, especially if you ended up doing one where there was a blur involved, where you have to look at all the neighbors and figure out what's happening with the neighbors relative to a particular cell. It's basically the same idea. Now, if you want to know information about cellular automata in particular to, or specifically for this problem that we're talking about, go read section 7.1 and 7.2 in this book called The Nature of Code. And it's actually very well written and interesting, and it talks all about how these things work. It gives you a little bit of information about a neighborhood. This happens to be a 2-dimensional one here. And then it talks about the one-dimensional, or instead of the 2-dimensional, the one-dimensional version right here, which is just going on a bit vector. Okay, so you are going to do the game of life based on an integer which represents the states of particular cells in this cellular automata. Okay, so that's how this one works. Go read that section and you'll get lots of information about that. Basically, we're going to represent a generation as a 64-bit unsigned long, and each bit is going to represent one cell in that this generation, in this automata. Okay, and if you have a 1, it means the cell is live, and a 0 means it's not live, and you're going to have to manipulate the bits as we go through this. Okay, now here's how it works. If you go read this before, you might want to pause the video and go read those sections before we get into the details here. But basically, a neighborhood in this case, instead of being like all around a particular bit or a particular cell, it's just to the left or right. So there's basically a 3-cell neighborhood here, which determines whether or not a particular bit is going to be live or dead in the next generation. Okay, and what we do is we actually take a binary representation of, notice by the way, there are 3 bits per neighborhood, right? And 3 bits you can represent with 8 different numbers. So 110 happens to be equal to 6, okay? And we will have a rule set that is an 8-bit number because 3 bits can create 8 different possibilities, 000, 001, 010, etc. And 110 happens to be 6. And if you look at the 6th bit in the rule set that we have here, 0, 1, 2, 3, 4, 5, 6, that's a 1. So if we ever get a neighborhood that is 110 for this rule set, it ends up being a 1 in the next generation. So this is all explained in the chapters above here, but that's basically the way it goes. Now, the way you run it is you basically say the automata program, and then you give it a number which represents this rule set, and you apply the rules for the entire two-dimensional piece as you go along. The first generation is always zeros, and then a 1, and then a bunch of zeros. Okay, that's the first generation. And then from there, you go on to the next generation, etc. Okay, let's actually run this on the code, and I'm going to show you it's a little bit different if we run this. Samples, automata solution, and it was 90, I believe, is what it was. It was 93, rather. 93, hang on a sec. There we go, 93. And I'm going to make this bigger so that it comes out right here. Let's see if we can do that. There we go. Now you'll notice this is not pluses. This is actually little boxes, so it looks a little different than the samples, the web page. But basically, the first generation is this line here, which I guess when I highlighted it disappeared. But the middle one is a 1. Okay, and then based on rule set 93, it says that, oh look, if it's a 0, what's it going to be in the next generation? Well, let's see, that was 90, so 93, let's see, would be a 1, so it's going to be a 1 in the next generation if it's a 0, and if it's a 0, it's going to be if it's a 1, it's going to be, looks like a 0 as well. But that's how that one works there. Okay, so it's not too bad. Again, not too much code for this one. You just have to spend the time to understand what's happening generation to generation. And it's just based on the neighborhood, and then the neighborhood represented in the actual rule set. Okay, so not too bad. All right, the last part of the assignment, by the way, you have to do 2 functions. You have to actually draw the generation, and then you have to do the advance to the next generation. Okay, the advanced one actually returns the new generation. Okay, for the next one. Okay, you can also, again, all of these code examples, you can use sanity check to compare to the sample output if you want, and it's better than actually trying to figure out the output just by looking at it. Okay, now the last part of the assignment is UTF-8. Now UTF-8 is a character encoding that was designed for to be able to be used across the world. Okay, the ASCII code, which we've talked about here, and you may have talked about in cs106b, is a 256 byte or 256 value code. In fact, it's actually only negative 127 up to negative 128 up to 127, and only ordinary letters, digits, and punctuation actually can be included. If you actually go and do man ASCII, you can see the actual ASCII chart here. Okay, and you can see that it only goes up to 127. Okay, and you can see that those are all the Latin alphabet, English alphabet, and it wasn't particularly good for people who want to write in other languages. Well, what's cool is that you can, we've created this new UTF-8, and there's also UTF-16 and some other encodings, but the UTF-8 says, great, now we're going to encode our glyphs, as they call them, characters in different languages, such that we can actually use them in our work. Now, C strings don't normally hold these directly, but printf can actually use them if the bytes are lined up appropriately to represent this UTF-8 code. Okay, and what it is you have this thing called a code point. Okay, and the code, there's over a million different code points, and the code point actually is represented by this hexadecimal number here that in this case is 4 digits long. Okay, and if you look at it, what you can do is you can actually print out if you give it hex 41, okay, that actually creates that actually goes and says, okay, looks it up in the table based on the thing we're about to talk about, the range we're about to talk about, and prints out the corresponding number. Now, if you'll notice something here, 41 happens to be the character in hex, a character uppercase A. Man ASCII will give you, if you look at hex 41 right here, it is actually uppercase A. What's cool about this UTF-8 format is that it's backwards compatible with ASCII. In other words, if you give it a byte and it happens to be ASCII, that byte will be represented as the ASCII value even in UTF-8. So it's pretty cool. But let's say we want a U with an umlaut over it. Okay, that happens to be 0xFC in our in UTF-8, and that's represented by 2 bytes, as it turns out. Okay, and those 2 bytes, FC will actually become 2 bytes that have a particular encoding that we're going to talk about in a minute, and that encoding is how it is actually represented in UTF code point format. Okay, so we have and let me actually show you an example. If you go to a web page, and if you go and type in UTF, if you go to Google and type in UTF-8 complete character set, okay, and right now it's the first link up here, UTF complete character list right here. If you go here, you can see all of the UTF-8 code points, okay, and the characters and the description of them all, and it's actually pretty neat. So you see all the ASCII ones down here, and then you can kind of go down and see some interesting other ones, and they've got things with umlauts, and they've got special characters and all that, and you can keep going down, keep going down, keep going down, and in fact they've got, like, it actually at the bottom of this page it says more. You can keep clicking and do that. Now, UTF-8 has the ability to do up to 4 bytes per encoding. We're actually going to only have you do 3, but let's take a look at how this works. Okay, let's take a look at the Cyrillic capital letter L. Okay, in this case, it is the code point is 041B. Okay, and if we look up here, the encoded byte is here. So if we go here and let's see, I missed it here. I went too far, but let's try this one instead. The Cyrillic capital letter E. Okay, if we go and grab this and 042D, and we type samples, and then UTF-8 solution, and then 0x42D. Okay, what it does is it says, okay, I know that that code point represents this encoded hex, which is D0AD, and guess what? D0AD is the bytes that are going to come out. Now, the question is, how do you get from 042D to D0AD? And by the way, it printed out the little backwards, or the little Cyrillic, is it here? The Cyrillic capital letter E, like that, printed that out, and that's kind of neat. It will print it out for you. But the question is, how do you get there? Like, how is this conversion done? Well, there's some rules for it. Here's how the rules work. Okay, if the code point is between 0 and 7F, okay, in other words, 0 to 127, it's ASCII, okay, which means that it's just going to be a 0 followed by the same exact bits that are here. Okay, so that's how you know. Now, if it's bigger than that, if it's between 80 and 7FF, okay, if the number of significant bits are 11 in this case, then it comes out as a 2-byte representation in UTF-8. And in fact, the first byte always starts with 110, and the second byte always starts with 10. Second byte is called the continuation byte, and continuation bytes always start with 10. And where does it get these other values from? It gets them from the value of the code put in. Okay, so if you look at this and you go, aha, I need to determine what range it's in, and then I need to fit it, and then I need to jam the bits into this format here, it's relatively straightforward. Okay, so if we look at if it's this range, if the range of the actual code point is between 800 and FFFF, right? We have 16 significant bits, and the first 4 are always going to be 1110. And then you'll have a continuation byte, which starts with 10, and you'll have another continuation byte, which starts with 10. Now, as we said, there's actually a 4-byte version too, but we're only going to have you do up to the 3-byte versions. Okay, so let's see how this works. There's a good example down here. If we want to do the euro sign. Okay, we look at the euro sign, and it happens to be the code point is 20AC. Okay, and actually, let's actually do this in here. 020AC. If you do that, okay, it says aha, it turns into E282AC, and it is the euro symbol, like that. Okay, well, how do we get that? Okay, well, we say what range is it in? We figure out what range it's in. Okay, that should be relatively straightforward. And then we say, aha, if it's in this range, we need 3 bytes. Well, where do those 3 bytes come from? All right, well, we can look at the actual 20AC, and this is how many bits we have in there. Okay, there happen to be 16 that are significant. And remember, we said that there were, in this case, there were 16 significant bits. Okay, and then what we do with that is we say, all right, now we know that those 16 bits are going to be divided across our byte, or our 3 bytes that we said, because we said we need 3 bytes. And how do we do that? Well, we say, all right, first things first. The first 4 bits in our first byte that we're going to output are 1110. Okay, 1110, and that's this part. That's going to be in any 3-byte UTF encoding. Okay, why is it doing this? It actually is doing this so that it can uniquely determine where bytes start and end. It's actually very clever. If you remember the Huffman encoding assignment from cs106b, you'll remember that had a similar kind of idea where you could read a bunch of bits off in that case and figure out exactly where the next representation came from. This is the same exact idea, and so it's very clever in that sense. All right, so the first 4 bits in that first byte for our 3-byte UTF encoding are 1110, and the next 4 we just grab from the first 4 bits of our 20AC value, and that gets plopped right in there. Okay, then we have a continuation byte. Continuation bytes always start with 10. So there's the first 2, but we have no decision to be made there, right? 10. And then the next 6 bits come from the next 6 bits here. Okay, so we said we started 0010, we got in the first bit, and then 1, 2, 3, 4, 5, 6. That will be down here for the next byte. All right, and guess what? We're left with 1, 2, 3, 4, 5, 6 bits left here, left with 6 bits left here, and the next continuation byte starts with 10 and then has those next 6 continuation bits. So really it's not too bad once you understand how this works. So play around with this. You're welcome to go to this page and grab any of the characters that you see here and try them out. There's a lot of fun characters that you may not have seen before. And you can see how this is actually put together by testing it with our sample solution and then writing it yourself. Now, you have to write 2 functions for this, you have to write 1 function for this code that kind of does 2 things. First of all, it's going to return the actual number of bytes that you are going to create. So you figure out that representation, what range it's in, and that's what it's going to return. That part's relatively straightforward. Then it has to take this array and it has to populate the array with however many bytes and the correct bytes that you find from the encoding. Okay, so it does 2 things. It takes in this code point value and it populates, it figures out what it's going to be, and it populates the array with those bytes, and then it returns how many bytes it actually put into that array. Okay, now the array will be big enough to hold the number of bytes, 1, 2, or 3, that you're going to produce. You don't need to zero anything else out, you just need to just the first byte is going to be, if it's a 1 byte, just fill in that first byte in the array. If it's a 2 byte, fill in 2 bytes. If it's a 3 byte, fill in 3 bytes, and return how many bytes you filled in with the result. Okay, so you can also, again, make sure you do sanity check on this. All right, you can check out the advice and FAQ page. It gives some good answers to questions you might have. We will update that during the week if there are good questions that come across on Piazza. So you should always go to that advice FAQ page first if you have a question about the assignment. Okay, as far as grading, you have the grading here. I don't need to go through too many details, but it tells you how to do things. Again, like assignment 0, you're going to fill in a README with answers to the questions for the code reading. Okay, and then you're going to also you're going to get 35 points for that, and then 65 points for the functionality of your actual code that you're going to write. Okay, and then you're also going to, it's going to be bucketed. You can read the details of how this works. As I said before, you get a bonus if you submit it on time. If it's late, you just don't get the bonus. That's up to you. There's no limit on how many times you can take that late. Sorry, I should say there's no limit on how many times you can get the assignment bonus. Every assignment will have that, and so you can do that. Okay, so that's the first assignment, and hopefully this helped out a little bit in explaining to you how it's going to work and what you need to do. And as always, put questions on Piazza if you have them. Thanks.